So I'm going to show you how to do a couple examples of both a system diagram and a force diagram using the description and using this checklist that's on the back of a lot of your packets, and it's on page like 76 or something of your notebook in the BFM section. So we're making a system diagram and then later on we're going to turn that into a force diagram. Notice these are two separate diagrams. So we're going to keep them separate in our heads. They're related, and we'll look at how they're related, but we need to think of them as separate diagrams that show the same information different ways. So to start the system diagram, we define a system, which will usually help to read this and look for the underlined word, and then put a dotted circle around that object to say, okay, this object is my system. This is the object of interest that I'm focusing on. Then we want to identify interactions happening right now, not in the past or future. So for example, a person's holding this ball in their hand. So I write the word hand and I show an interaction between the hand and the ball. And then one object that's always interacting with everything is the planet Earth. We call this interaction gravity, but the object is called Earth. So we show an interaction between the Earth and the ball, and an interaction between the Earth and the hand. This system diagram is done now. This shows all the interactions that we need, and we can move on to the second checklist item. The number of objects interacting with the object of interest in the system diagram is the same as the number of arrows in the force diagram. So I can tell there's two objects interacting with the ball, the hand and the earth. That means there's two arrows on this force diagram. I usually start with the arrow for earth because I know that the earth always pulls down no matter what. We can even take a note on this over here. Earth always pulls down. This is like on the planet's surface. If we went up into space, then it might be a different consideration. But this arrow downward we call F earth on ball. This, by the way, is the third checklist item. I usually go back and forth between these. I'll add an arrow, look at the object, and then name it. F earth on ball. The object of interest is second in the name, so I know it has to be earth on ball. And then I look at see what the other object is. Looks like it's the hand. So I'm going to draw an upward arrow because the hand's pushing up on the ball. F hand on ball. And I've done this for both of my interactions. Last checklist item, this can be a little tricky. The direction of all arrows makes sense, and constant motion means balanced force. Show equal forces with congruency marks. Notice this object is not moving at all. It's staying at rest. It says it in the description, and there's a dot next to it that means at rest. So that's a definitely example of constant motion tug of war, or sorry, balanced force tug of war, because it counts as constant motion. So I'm going to show that with two congruency marks. This example is done. We're going to move on to some other examples. I'm going to skip some because they're kind of interesting. But let's go ahead and move on to question 1B. Again, I'm going to draw the word ball, define it as a system. Then I know that this ball is interacting with the floor or the ground. Doesn't really matter whether I call it the floor or the ground. And there's a hand, but the hand is not interacting with the ball right now. Notice this says interaction is happening right now, not in the past or the future. The hand probably interacted with the ball at some point, but it's not interacting with it at this moment. In fact, it says after a person misses the rebound, so maybe this hand didn't touch the ball at all recently. So I'm not going to draw an interaction from the hand to the ball. I do still need to draw the word earth, and notice the earth interacts with everything. But just like in this example up here, this ball is only interacting with two objects, the earth and the floor. So I'm moving on down to this. I know there's got to be two arrows because there's two interactions with the ball here. And I'm going to draw those two arrows one by one. F earth on ball. And then the floor is interacting with the ball as well. Now, this is where I need to think carefully. Constant motion means balanced force. This does say the ball rolls at a constant speed in a straight line, just like ruler ball. So this looks like it's an example of constant motion, which means it has to show balanced force. Constant motion equals balanced force. That was kind of easy here because the hand was obviously pushing up on the ball, but the only way to balance this F earth on ball to make the speed stay constant is to draw an upward arrow that is balancing F earth on ball. And that has to be F floor on ball, because that's the only other object that's interacting with the ball. Now, you might be asking, like, hey, why isn't there an arrow pointing forward? Because this ball's moving forward. Shouldn't that show force pointing forward? But what I gotta restate over and over and over again, a force is an interaction between two objects. We are looking at the interactions between these objects and the ball. And there's no interaction pushing the ball this way right now. It's moving that way, yes. But we've seen again and again, constant motion means balanced force. If you want to speed up this ball, then yes, you have to push it. If you want to slow it down, you have to push it. But constant motion means balanced force. Let's look at some other interesting examples of this. I'm actually going to flip over the page and let's do this one here. This is similar actually. There's a ball, there's the earth, and there's a hand. The ball is my system, the earth is exerting force on both of these things, and there's definitely an interaction between the ball and the hand. This example is slightly different because I have numbers that I need to work with. So let me pay attention to these numbers. It says a person catches a medicine ball by exerting 100 N upwards. This N stands for newtons, and it's the unit of force. So the hand is exerting 100 newtons upwards, while the earth exerts a force of 45 newtons downwards. So that means that this arrow, F hand on ball, F hand on ball, has to be longer than the other arrow, because this arrow equals 100 newtons, and this arrow is only 45. F earth on ball equals 45 newtons. So I can tell that this arrow is longer than this arrow because of the numbers and also because of the length of the arrow that I drew. That is, by the way, related to this. This is where the direction of all arrows makes sense can get really tricky. Because I know from looking at this picture that this is not constant motion. This ball is being slowed down by the hand. So I know that I can't show congruency marks because unlike this example or this example where there is constant motion, constant zero motion or constant straight line motion, this doesn't show constant motion. This ball is decreasing speed. So this question is asking, which way can you push the object to cause the change? If I imagined a ball coming at me this way, moving in this direction, so like my fist right now is the ball, which direction do I have to push it to get it to slow down? Well, I have to push it this way. The ball is coming at me, I have to push it that way to get it to slow down. If it's coming even faster, I have to push it harder to slow it down. Now, that's what this force diagram is showing. It might seem like there should be more downward arrow than upward arrow because it's moving downward, but that's not the connection between force and motion that we've seen. We've seen a connection between force and motion where if something's moving and we want to stop it, we push it in the opposite direction than it's moving to slow it down. So one last example here. Let's just show how this one works. we have a more complicated system diagram because we're looking at the skateboard, or we could just call it a board if we wanted. We know that the earth is important. We know that there's a person riding the skateboard. And we also know that the ground is important. So let's define our system as the skateboard. Let's draw an interaction between the earth and every single other object. Let's draw an interaction between the ground and the skateboard. And it looks like the person is interacting with the skateboard also, but not interacting with the ground. So now we got to figure out how these arrows work. I'm going to start with F Earth on board. I'm just actually going to abbreviate FE on board. Then it looks like the person is pushing down on the skateboard also. This says, which way could you, Does the direction of the arrow make sense? If my hand is this skateboard and like someone's standing on top of my hand, ouch, I can definitely feel the person pushing down on my hand. So that's convincing enough to say, okay, F person on board, I just wrote FP on board to make it easier, is pointing down. Now, I'm noticing this says constant velocity. That's similar to saying constant motion or constant speed. So I know this has to be a balanced force diagram. And the only direction the ground could be pushing to balance these forces and make this a balanced tug of war would be upwards. So I guess that makes sense. The ground is pushing upwards on this board, just like the ground was pushing upwards on this ball. So I'm going to make this arrow nice and long. I'm going to label it FG on board, and then the last thing I'm going to do is show congruency marks to show balanced force. So essentially this longest arrow is equal to this arrow plus this arrow. So I could do that, for example, by putting a dash on this line, putting a circle on this, and then putting both a dash and a circle on this together. This is showing balanced force just like this is, but it's showing 2 against 1. That, by the way, is explained further in BFM 5. If you didn't quite get these congruency marks, BFM 5 is a way to understand congruency marks.